The following program is brought to you by Caltech.
I've been very fortunate to be able to work with Carver in three eras of his life and my own. Similar to Chris, the first was in being a student of Carver's at Caltech. The second was in forming a company where Carver was founding investor and board member and carried us all the way through to an IPO. And then a third stage, which has been working on the quantum physics project. So I'd like to tell you about those three experiences. The first one, basically, my life was changed forever when I read this paper. I was a student at Simon Fraser University in British Columbia. Perhaps, I'm not sure how many people have ever heard of that university, but it's a small university up in Canada. I'd been trying to figure out how the ear works. I was interested in music, how we could hear the notes out of music, and had understood that there was something about the way the cochlea was processing sound that was different and better than the fast Fourier transforms that we were using as engineers. And I'd been struggling on my own for about a year to try and figure out the filtering process in the cochlea. I knew that it was a traveling wave, and that's about all I knew. I was trying to do it intuitively from that point. And one day I was walking past a friend's desk up at Simon Fraser University, and I saw an IEEE journal on his desk. And I have no idea what made me do this. It's not like me to reach onto someone else's desk and do anything, but I did. For some reason, I reached over and I just flipped this journal open, and it opened to this page. This is a true story. It opened to this page. And I said, oh my God, these guys are doing the work that I want to do, and they're doing it right. They've studied the biology. And they've built chips and devices based on how the biology really works, not just my guess about, intuitive thoughts about it. They've really studied the biology. They've gone and done the math. So I figured out, now, this may surprise some of you since we're here at Caltech. I had never heard of Caltech. So I was living under a rock, apparently, for my entire life. So I didn't know anything about Caltech, so I thought, well, I'll just call this guy up. So, like Chris, I got Helen Duravan on the phone. Now, I had to run the gauntlet, as Chris did. What Helen said was, he's really a very busy man. But I want to talk to him. I've got some ideas about how the cochlea works, and I could build a post-processor that could build on this. And after about 3 tries, finally Helen said, okay, well, maybe send me something in writing and I'll give it to Carver. Carver apparently said, okay, I'm interested to hear what you have to say. Let's meet in Portland, Oregon. I'll be up there with my students at an industry conference. Let's have a chance to chat up there. When I went there, I saw for the first time the impact that Carver was having on the industry. This was a formal IEEE conference. There were people there from Nippon Electric, NEC. The major industrial corporations were all looking very carefully at the early work in VLSI Neuromorphic and saying, this is going to change the industry. This is something that we want to be a part of at an early industrial scale. And at that time, not only did I get to see Carver's talk, something else that profoundly impressed me was meeting Carver's students. So at that meeting was John Lazaro, Toby Delbrook, Misha Mahawald, and John Harris. Those 4 students blew me away. I'd never been in the room with people that were that far above the level that I was at. So I couldn't believe it. And this was his students. This is Carver's students. So basically, I'm here, these guys are here, and Carver is up there in the clouds somewhere. I couldn't believe my good fortune, to be able to meet these people. And I knew, okay, this is it. This is what I want to do with my life. This is where I want to go. This is the person I want to study with. I was very fortunate. Carver accepted me into the program, made it possible for me to go to Caltech. I worked on the cochlea. Carver, in this book, put together a massive vision about building brain-like systems in silicon. And it wasn't just the cochlea. It was the whole brain, wafer scale integration, retina, silicon neurons, floating gate technologies, and the cochlea. There's a recurring theme here where I thought, this is all more than I can do, but more than I can help with. But I could probably help on one piece of it. Let me see if I can help on the area of the cochlea. So I dug in on the cochlea, was inspired by the work, and inspired by Carver and Dick's collaboration. Clearly, this was a wonderful collaboration that was happening with Dick Lyon on building these cochlea, low power floating gate or low power circuit. So I began working. At first, started building cochlea chips that were very much like the original designs. One word that very much impressed me in that original 1988 paper, the layout was done. It was, the cochlea is a cascade of second-order sections, and the original cochlea designs that they described there were laid out in a boustrophodonic arrangement. You may recall that term, Dick, in the boustrophodonic. What that means is serpentine. That they would build this long chain, but if you're going to build a long chain of 200 stages and a chip that's square, how are you going to do that? You fold it up, fold it back and forth. So boustrophodonic means serpentine. I thought, I'm going to get to go to Caltech and learn words like boustrophodonic. Yeah, that. Okay, so now one of the troubles with this boustrophodonic arrangement was that there were only like 30 pins or something on these packages, right? So what they would do is that they would put 100 stages, but they would go in by 5, out by 5, and then put a pin there. And then in by 5, out by 5, and put a pin there. So they would basically bring out every 10th tap of the cochlea. The early designs were like that. That meant that they couldn't characterize every one of the stages. Well, when I got down to Caltech, I saw Misha and Toby working with creating these images out of the retinas, and they had all this fabulous infrastructure, the scanners, the serial analog multiplexers that would allow you to get every single pixel out of, multiplexed out of the retina. And so I remember about 3 months in, I was groping around, kind of like what Chris said, feeling like, am I really doing anything useful here? But then one of the first things that I remember saying was, could we put a scanner on the cochlea? That hadn't been done before. And then we could instrument out every single tap. And then we could characterize every single tap and get much better statistics, not just every 10th tap, but every tap. And now we could really see how the matching looked. And not only that, but if you take out every single tap, now you could make a movie out of what's happening inside the cochlea. You could scan every single line out. And so here's what the movies, one of the movies of the cochleas look like, just brought out onto an oscilloscope. And so the top bar is the pressure wave in the cochlea, and the bottom wave is the membrane displacement. So now you see if we're putting in a low frequency wave, the membrane displacement, the activity is happening at this particular location. If we speed up the wave, now the activity moves over. This is the famous frequency to place mapping of the cochlea. That if you put in a different frequency, you light up a different place of activity on the cochlea. This is how you hear. This is how you can separate low frequencies and high frequencies using a mechanism that looks like this. And for the first time with a scanner on a cochlea, we could actually see the wave. So I was thrilled. Okay, finally, I'm beginning to make a little contribution here. And so there was many exciting moments where I got to see that look on Carver's face of some progress that was being made. We were able to make not only the one-directional traveling wave structures that Dick and Carver had originally conceived, but then we were able to make bidirectional traveling waves that modeled the fluid in a fully traveling wave mechanism that could go in both directions and so on. So there were a number of, so that was an extremely exciting time. I always hoped when I was at Caltech that someday I would be able to form a company that would build on this type of technology. In 2000, same timing as Chris, I formed a company called Applied Neurosystems that later, thankfully, got a much better name, Audience. AppliedNeurosystems.com was just too hard for people to type, but Audience people could type. And the idea then was we were going to try to reverse engineer not just the cochlea, but the entire hearing system in the brain. And in this, we would not only do things like speech recognition, but we would also separate the sounds that you hear. For example, right now you're hearing my voice, but there's also creaking chairs and a fan and so on. And somehow those sounds aren't stopping you from hearing my voice. You're separating the sounds and then recognizing what I say. All of that machinery is being done in this green box, this stream separation, which is being done largely in the brainstem and the lower parts of cortex. And we reasoned if we could just do that and put that on a chip, it ought to be good for something. But we didn't know what. And boy, it took a long time to figure out what that would be good for. Now, when we started the company in 2000, we had an idea. Stream separation would be what it would be good for. But so what do you do with that? So I had an original business plan that said, better voice dialing for your cell phone. Now, you remember in 2000, so who voice dials your cell phone? And nobody did, even in 2000. But it said something very important to the venture capital community. I used the word cell phone. That was very important, because at that time, that was 400 million units per year. So all we really had to do, you have to give two numbers to the VCs. We said 400 million units per year, and we're going to sell a $1 chip to each of them. That would be $400 million per year that we could make. To multiply those two numbers together, that's a big enough number to make the VCs say, OK, we'll put something in. So they were supportive. Carver agreed to do seed investment here, put in $100,000 to help get the thing started. We had Paul Allen, who also invested. So I had a couple of heavyweights on the team. And by 2005, we had a technology that was good enough that we could actually solve this problem in a meaningful way, and something noticeable changed. Do you remember the cell phones of 2005? They were just flip phones with a little keypad on them. You dialed them. You placed phone calls on your cell phone. That was it. The phones we have now, we call them smartphones because they're also web browsers, and they have operating systems and cameras and all this stuff. The cell phone that we have nowadays is very different from the 2000 era cell phone. When did that change? 2005. That's the time that Apple was getting ready to release the iPhone. And nobody knew this except me. I knew this, a little secret that I knew that I had to keep secret for a couple of years, because I knew Andy Rubin, who became the head of Android. He was the head. I said, we should go talk to Andy Rubin and tell him what we're doing, even though it wasn't public that Google was going to get into the cell phone business. And so Andy said, you're making 2-microphone noise reduction for cell phones? That's going to be kind of important. I'm going to tell you something that I can't tell anybody else right now, or we're not telling publicly, but it'll come clear in a couple of years. But we're going to be in the phone business. Google's going to be in the phone business. And we've been thinking about 2-mic noise reduction for cell phones. Looks like you're going to have a pretty good way of doing it. How about if we just use you? I said, that would be just fine. Yeah? That'd be OK with me. Yeah. So we got a lead. We had an early customer, and we showed up in their first Google Experience phone, the Google Nexus 1. And that put us in a competition situation where Apple needed to be at parity there. So we found ourselves in a good position. By 2010, we were in important phones coming out of Cupertino and Google phones. And so the company was actually able to get commercial footing, all based on the original beginnings of cochlea-based chips. Low power signal processing for chips that did finally ultimately make its way into cell phones.
What's that thing on the right, Corey?
Oh, so the thing on the right is the die plot of the chip. See these big circles here? Those are the pads. It's not the usual pad ring around the outside. Those are the pads. It's a special packaging they use in the cell phone business. OK, so I'd like that experience of starting the company. So like Chris, that's been a 14-year odyssey. 2000 to 2012 was the IPO. I'd like to take 2 minutes to show you the trailer for a little movie documentary that I made a year or so ago. I'm going to show it to you because it has little features of Carver being interviewed in it. Carver gets to say some cool stuff, so I'd like to share it with you for that reason. Now, I'm hoping that the audio is on as it was before. So let's see, we'll skip past the demo of it. Here we are. Maybe some volume.
Now that Audience has gone public, there's a lot of interest in the early days of the company. What was I thinking when I started the company? It ended up becoming the premier 2-microphone noise suppression company for cell phones. But did we know that at the time that we started the company? My original personal motivation came from being a self-taught musician. Could we write a computer program that could figure out what notes are being played? Could we reverse engineer this part of the brain?
I said, okay, if you want a lead investor, I'm in.
And Paul was really impressed. I want to do $1.5 million.
I said, is the Pope a Catholic?
I remember telling Lloyd, don't be greedy.
It becomes a technology looking for a market.
It was extremely frustrating.
Now I was on the wrong side of the third wealthiest man in the world. Microsoft, with their massive research team, is saying, you've got something that we'd like to have.
Peter had figured out that voice quality was a marketplace. The company that can solve that problem has a place in every cell phone.
Okay, so that encompasses the 14-year experience from kitchen table startup, wandering in the dark, not sure what we're going to do, to IPO. That's an experience that would not have been possible without Carver's involvement from day one. Carver, I want to thank you for that. It's life-changing. It took me all the way from student at Caltech up to that point. So Carver, my sincere thanks for that experience. Now, I have the third era of my work with Carver is a complete change of direction, and I'd like to take the remaining 5 minutes to talk about that. Am I still on? Still 5 minutes? Good? Yep. Okay, good. Okay, so now it's a change of direction, but there is some temporal overlap to it. So, of course, it's already been mentioned that Carver wrote this beautiful book, Collective Electrodynamics, published it in 2000, and of course I read it as soon as it came out. And like the first book, I thought, yeah, I really got a lot out of that. And then a year later, I read it again. I thought, oh man, I really didn't understand it the first time I read it. Now I get it. The third time I read it, I thought, the first 2 times, didn't. But the 5th time, I think I started to get it. Like the first book, there was more here than I could possibly contribute, make a difference on. But after the 5th reading of it, over a period of years, I felt there's a small area where I think maybe I can help. It was in the area of the quantum transition. And I'm going to read three or four quotes here that are relevant to this. The coherent world has continuous wave functions and abrupt but continuous quantum transitions. Now that simple sentence, that flies in the face of modern belief about how light is generated in an atomic transition. It's supposed to be a random event that happens instantaneously and it kicks out a photon at a random direction. That innocent-looking statement there, abrupt but continuous quantum transitions, is a big deal. Carver is saying it's not like the way you all think it is. That's different. To arrive at this picture, we had to give up the one-way direction of time and allow coupling to everything on the light cone. That's another very big deal. So that means time flows in both directions. That's huge. That's a really big deal. The future influences the present and the past. So big deal, but it's part of Carver's picture of how the universe works. The electron wave function depends on the potential. The potential depends on the charge density that is determined back by the wave function. So we have an inherently nonlinear problem. It's circular, which means to solve it, you have to go through a nonlinear iterate to consistency. That's a big deal too. Every one of these things, each sentence here is a big deal. And to try and actually execute Carver's vision, it's an overwhelming task. The last one, very important. Conceptually, the continuous charge distribution of the electron wave function is much more understandable than are the multiple levels of infinity that result from point charges. I left that one for last because it's so important. Carver has been pounding on the idea of the deep problems from quantum physics. It plagued the last century. It's a long time to plague an entire field. have at their root the problem of a point charge assumption, that it's a wave, not a point charge. And he's unrelenting on driving that point home in the book. So I thought, okay, the cochlea wave mechanics, where I learned I found that I could make a contribution about cochlea waves, turn out to be related to quantum wave mechanics. I thought, maybe I can help. If I could help on the cochlea and its waves, maybe I could help on the electron and its waves. So I became interested in that. And I spent about 10 years trying to find a way to help. That's a long time to try to help, and didn't make much progress. I tried and had many enjoyable discussions with Carver about it, but none of the attempts actually worked. In 2012, Audience went public. 2013, I retired from Audience, and I got married. My lovely wife Isabel is up there. Isabel has been supportive since getting married and since retiring from Audience of my working on quantum physics for the last 6 months. In the last 6 months, my fortune has been different. I've actually started to make progress. I found a way that I could get traction on this problem. So I'm going to briefly tell you that. This is the usual view of how light is emitted from a hydrogen atom. So the emitting atom starts in a high energy state, typified by this electron wave function, 2p state. And then at some random time, it jumps down into a low energy state, this 1s function, and it kicks out a photon in some random direction. And everything's random, as Bohr famously debated with Einstein, as Carver famously says, Einstein was right, Bohr was wrong. He's clear about that. Thank you for that. The clarity is extremely important. It comes down clearly. Carver says, this is wrong. This is not how it works. It can't possibly be this way. There's no random number generator anywhere inside the atom. It must be an interaction between two things. This is my schematic of Carver's view. So forgive me for I'm visually paraphrasing, but I hope that this captures the essence of it, that the emitting atom undergoes a transition from the 2p state to the 1s state, and the absorbing atom goes from the 1s state to the 2p state, so it absorbs the energy, and this energy is this is the abrupt but continuous transition. Right? It's not a random jump at an instant time. It's a smooth transition that occurs when these two atoms find each other, communicate somehow by a transaction, and agree that they are in phase with each other, exactly the right phase, so that they fall in love and they share a photon. Okay? So the transaction occurs between them and only them. It could happen anywhere. These two find each other by their magical phase relationship, and that initiates the transaction. This is a big deal. Now, it's a big enough deal that they're finding each other and all this. It's an even bigger deal. Not shown here is the fact that that could happen separated by 100,000 light years. So next time you look up at the stars and see a star that might be 100,000 light years away, in order for this bold statement to be true, that star 100,000 light years away would have to know that you would be looking up 100,000 years later when it emits that photon. So the bidirectionality of time is a mind bender. Very big deal. Okay, but anyway, this imagines that the two atoms are close to each other, and so the time travel aspect of this is not factored in. Okay, so now this view of a transaction between two atoms is something I thought, this is a little bit similar to the cochlea waves. I've got an initial state and a final state. In Carver's book, he used coupled resonators, an analogy, in order to be able to show the principle, because this was just one of many points that he was trying to make. So he did a first-order analysis using coupled resonators, and I thought, maybe I can help. Maybe I could try to do this problem over again, but with coupled atomic equations. Okay, well, the atomic equations that would be relevant here would be the Dirac equation, not the Schrodinger equation, and that's the best previous theory to get the wave functions and the energies. So that should be easy, right? I should be able to at least look that up. That was 1928. That should be easy, right? No, it's not easy. Now here's where it starts to get interesting. The Dirac hydrogen atom in 1928 was able to predict proper levels, and at least appeared in 1928 to predict all the levels correctly, but it has serious problems. The wave functions are singular. That means they go to infinity at the origin. That was known by Darwin in 1928. And the energies are slightly wrong. That was discovered in 1947. So 20 years later, they discovered the energies weren't quite right. That was by Lamb and Rutherford in 1947. That's known as the Lamb shift. That's very important. The Lamb shift required an explanation. And that explanation came from Hans Bethe in 1947 and Richard Feynman in 1948. It's the work for which Richard Feynman won the Nobel Prize. The Lamb shift problem was solved, I'll use the air quotes for that, it was solved in 1947 and 48 by renormalization, which says you add a self-energy from a point charge of the electron, which turns out to be infinite, and then you subtract a reference point charge, self-energy, which is also infinite, and then you rescale the mass. So let me get this straight. Your solution to get this tiny correction is to add infinity, subtract infinity, and then divide by whatever you need to get the right answer. That's renormalization in a nutshell. Carver says, in a nutshell, that's hogwash. If that's the right answer, something's wrong. I agree with him, but nobody has known what the right answer is. So, it produces a corrected energy, not a corrected wave function. Consensus. There is a big problem. Richard Feynman himself, in his Nobel acceptance lecture, said renormalization theory is simply a way to sweep the difficulties of the divergences of electrodynamics under the rug. Paul Dirac, from the Dirac equation, said, this so-called good theory involves neglecting infinities which appear in its equations. This is just not sensible mathematics. Sensible mathematics involves neglecting a quantity when it is small, not neglecting it just because it's infinitely great and you don't want it. Okay? So the giants of the previous century, the Nobel Prize winners, are saying, we did something, we got something to work, but we know it's not right. The physics at its core is not right. Carver, in his book, sums it up very nicely and adds a hint about where the solution may be found. The idea of a point particle brought with it infinite energies that must be renormalized away. Degrees of freedom in the vacuum brought even more infinities and made a sensible theory of gravitation impossible. The path has been, as Einstein predicted, lengthy and difficult. The challenge now is to put all of that behind us and to start anew. Carver doesn't just lament the problem. He also says it's got something to do with those point charges. It's the root of the problem is the point charges. Now, this is where the problem has stood for 70 years. And it's a big deal. It's an unsatisfactory element of all of 20th century physics. So it's an unsolved problem and a giant opportunity for all of us to get to the bottom of what's wrong. But it's still not solved yet. Now, after I got married, my lovely wife said, it's okay if you want to work on quantum physics for a while now. You've earned a break from having run a company started a company and got it to work for 14 years. I came across a paper that had a very good idea in it by a guy named Vladimir Kalotviansky. I'll give you the quote in just a second. But there's a very simple idea. You had a point charge, it's the electron. But in a hydrogen atom, you have two charges. You have the electron orbiting the nucleus. The proton at the center is also a charge. And in the Dirac hydrogen atom, everyone is expecting the electron to create a wave function. The solution will be effectively a charge cloud around the proton. Okay, so in fact, the electron is no longer being modeled as a point charge. We've got a wave function there that's doing pretty much what Carver wanted. There's a wave function, and you can regard it, interpret it as a charge density. But wait a minute. The nucleus, in fact, is being treated as a point charge. Aha, that's the problem right there. The point charge is the proton at the nucleus. Kalotviansky, in 2008, said, wait a minute. If it was a two-body problem, like the Earth orbiting the sun, everybody knows that the Earth goes around the sun. Yeah, but the Earth tugs a little bit on the sun, and it forces the sun to move a little bit. The same thing would happen in an atom, that the electron would pull a little bit on the proton and jiggle it a bit. So even if it started out as a point charge, by the time you had the electron cloud, it would be moving. It wouldn't be a point charge anymore. That's a good idea. So now, once I saw that and realized maybe I could work the math on that, I looked and saw Darwin had recognized this deficiency in 1928. This is the grandson of the great Charles Darwin, the evolutionary scientist. Charles G. Darwin, his grandson, said, "The solution reveals a small blemish in the equations, for we have to admit the existence of proper functions which become infinite. Of course, all integrals connected with the spectrum are amply convergent. We do not perhaps know enough about the essential rules for proper functions to pay much attention to this deficit, that is, the infinite wave functions, but it may well be that this problem would go away if we could solve the problems of two bodies properly. The atom could be regarded as a two-body problem. Nobody solves it that way. I think that is an opportunity. And 6 months ago, I said, I think there's something there. I think we could treat this as a two-body problem." This is Kalatviansky's quote. "Everybody knows that the atomic electrons form a negative charge cloud within an atom. Few, however, know that a similar cloud is formed by the atomic nucleus around the atomic center of inertia. The positive charge cloud is just smaller in size. It's rescaled to the distances of, as stated there, but it's exactly the same nature." Both of these are saying basically the same thing, one in 1928 and the other in 2008. It's a two-body problem. And if we solve the two-body problem, we might be able to get the infinite wave function tamed to become finite, and it might give a small energy correction, a 1 part in 1 million energy correction that could give a proper explanation for what Lamb observed in 1947. That was my hypothesis 6 months ago. So I began working on that with Carver's blessing and support and encouragement. And this is my final slide. This is a summary of what I found. This first picture here shows what you would normally expect. If you normally assume that all the charge density of the nucleus is a point, it's a delta function. So you have your point charge. This is the problem of the nucleus. The Coulomb potential is shown here, which is singular. So you have a 1 over r potential, and the solution is an e to the minus r electron wave function. This is where people normally stop. And everything about this is singular. You have a point charge, you have a singular Coulomb potential, and you have a wave function that has a cusp. So every one of these three colored functions here has a singularity built into it in some way or another. But if you say that you allow the nucleus to jitter in a way that is a mirror of what is happening with the electron, now you have two things that are moving together, and now there's no need for any infinities anymore. The net result is the nucleus is now no longer a point charge. It's got a little charge distribution. It's like a scaled down version of the electron charge. And now the Coulomb potential that used to go down to minus infinity now has a nice finite bowl, because the charge isn't all in one place. It's distributed over a little area, so you have a finite bowl. And the net result is it perturbs the wave function. You now have this nonlinear circular problem. And the wave function, instead of having a very pointy top, if you zoom in at the very top, you see this picture, and it's rounded off at the top. So it has made all the infinities go away. It's put a tiny shift in the electron energy. This is the amount of the electron energy shift. It's about 1 part in a million of the ionization energy. It has the right sign. Here's a summary of the results. The modified wave functions and potentials are well behaved. They're tamed near the origin. The singularities and the cusps are eliminated. The energy shifts have the correct sign and the magnitude for the ground state. Most importantly, we're eliminating or avoiding the old infinities. Rather than living with an existing infinity and adding 2 more and rescaling, that's, 4 wrongs doesn't make a right? We're going back and fixing the first wrong. And it so far appears as though this might be the thing that was eluding perhaps even Feynman and Dirac over the last century. I would have to say it's not proven yet, but it's a contender. It's a contender to explain that 100-year-old mystery. Now I want to thank you one more time for giving me the experience of going on that Easter egg hunt. That is a fun thing to go search for. I would never have known to look if Carver had not said point charges. Century-old problem, big deal. Carver illuminated this path 14 years ago. It's taken me 14 years to figure out what to do on that illuminated path. But he illuminated the path 14 years ago. It's a phenomenal contribution, Carver. Thank you for that, and happy birthday.
I should, can you hear me okay? Does that work? Yeah. Lloyd, my fondest memories of Lloyd are when we started working on the cochlea. It's a tough analytical problem. And the models that people had were really pretty rudimentary. And there was a guy by the name of De Boer?
Oh, yes, Egbert de Boer.
Egbert de Boer over in
Netherlands.
Netherlands,
Yep.
right? Who was the expert and really had done all the good stuff there. And he had a theory, and Lloyd dug in, and the first time I knew there's something special about Lloyd was when he, I was checking up how things were going, and he said, "Oh, I have it here in my Mathematica notebook." Well, I had tried to use Mathematica back in those days. Mathematica was orders of magnitude more crufty than it is today, and so then I began to realize Lloyd was really digging into this stuff. So Lloyd is one of these people that just digs in and doesn't let go until it's done. And I'm delighted you're headed there. So thanks for all the good work. And then we're going to hear from Jamil.
Yes.
Great.